logical address and physical address. We have also seen the different hardwares required, what is paging concept, what is the concept of pages, segments. So if you missed out any of the session, then I advise you to please go through the previous recording, which is available on the platform. So you can have a proper revision of that. And also the second part, which we have gone through, is based on architecture perspective, where we have worked out on different aspect of theoretical as well as some numerical examples also. So we have elaborated in terms of time constraint, in terms of different miss and hit operations, and as you can refer, or if you have been in the classes, so we have gone through to understand what is the correct structure between cache and main memory as well as in secondary memory, and how CPU gets data from any of this access. So there are different options available. So I hope you have a comfortable revision of that also. And if you feel so any queries, so you are most welcome. You can put in the forum itself. So now we are going to start the next unit, that is unit 9 and 10 as well. That is vector processors. So all modern computer systems, right, they supports this vector processing features. And the main objective, as you can see in the introductory part, that the vector processing performs the arithmetic operation on the large array of integers or floating point number. So being a general purpose computer, so we perform the operations one by one or based on the logics that has been implemented. But if we have the options of vector processing that you can see over here, so it performs the arithmetic operation on large array of integers. So soon we are going to elaborate what do you mean by large array of integers or floating point numbers, right? So the learning objectives are that you will be able to understand the vector processing and its advantages. We'll also explore different characteristic and features of vector processing. We'll look out the types of vector processors. And as earlier in unit number 2, it has been taught to you that we can have parallelism through different types and levels. And one of that is SIMD, that is single instruction and multiple data architecture. So that we'll also explore, because this is a subsequent unit number 10 as per your syllabus or as per the contents which has been given to you. And I request that you may please raise your hands whenever you feel so. If you have any doubt in between, you can raise your hands, and time by time I will check it up. And if possible, then definitely we can have the resolution of the queries if time permits. Let me start with this slide. I don't have the blank slide today, because earlier I used to go through the numerical questions. So now I have the contents ready with me. So we'll try to explore, and whenever we feel so to elaborate, then definitely we'll go ahead. So we want that computers can solve mathematical problems, and obviously yes, it is one of the one of the basic functionality of a computer system to solve not only mathematical problem but a tons of problems, depends on different areas. So, but as far as this part is concerned, we'll focus on how mathematical problems can be solved, especially arithmetic operations on the large array of integers or floating point numbers quickly. Okay. So as you know that we may have different options, and like suppose you can go to the second point, that in general purpose computer would use loops to operate on an array of integers or floating point numbers. Like suppose we need to have a addition from say 1 to 10. So it may be possible that we need to go through a cyclic approach or a loop approach, and then we can add two integer numbers, and then the result can be stored to a separate number or register. But for large array, using loop would cause overhead to the processor. As you know that we want efficiency, we want the relevant results, so we don't want that there should be overhead in terms of mathematical calculations. So that's the third point. And let us see the solution. So to avoid the overhead of processing loops and fasten the speed up the computation, parallelism must be introduced, as we have gone through a very detailed session in parallelism. Now let us focus on our topic, that is vector processing. So vector processing operates on the entire array in just one operation. So learners, this is very important statement, right? You may also have a note of this, that this vector processing, operates on an entire array in just one operation, with a condition, obviously, that that array elements should be independent to each other. If they haven't dependent to each other, then definitely the answer is no. But if they mimic this property, that they are independent to each other, then definitely we can have a operation in a single go, and that seems the beauty of working with vector processings. So the idea is it operates on elements of the array in parallel. Now vector processing is possible only if the operations performed in parallel are independent. So this is, I can have an asterisk over here, because if they are independent, then only we can have the vector processing. Otherwise, it will not be possible if they have independent to each other. So there are a few other points to understand and to consider. Then we can go through the structural part also. So a processor can operate an entire vector in one instruction. So let us go through what we mean by vector over here. Now work done automatically in parallel, that is simultaneously, assuming that all the data variables, they are independent. The operand to the instructions are complete vector instead of one element. All right. Now it reduces the fetch and decode bandwidth, and obviously it achieves data parallelism. As we have seen that we may have three types of parallelism. So this is vector processors can be taken as an example of what? Data parallelism. Now task usually consists of large active data sets. So what I said, that this is meant for the mathematical aspect, the mathematical computation aspect, and especially for integer, if we have a bunch of integer numbers, and if we are having a float numbers, like suppose you have two registers b and supposed to be added by c, and the results should be stored in a register a, and this is not for a single value of b and c. You have multiple instances of the variables b and c, so either you run in a loop, or either you can go on a single shot, assuming that they are not dependent to each other, different instances. So and I have also hoped that during my previous classes, where we have worked out that how the parallelism can be achieved, you may be able to get it, that how we can done through the data parallelism also. So the task usually consists of large active data set, number one. The poor locality, okay, this is very important, because we have gone through the topic of locality of reference. Locality of reference. So I will love to hear from you, and just want to see that are you capable, are you able to understand what is locality of reference, because this is one of the topic that we have discussed in our previous classes, and this is one of the very important topic in computer science terminology also. Either you are learning operating system subject or some other advanced subjects, you may come across number of time locality of difference. So I hope so, students and learners, that you know this topic. If the answer is yes, very nice. If the answer is no, still very nice. Simply you need to devote 10 minutes to the previous videos, okay, and you will learn. So locality of reference gives an edge to computer scientists or to computer people, that if suppose there is a point, there's a data, and the next data we can find it out in terms of spatial locality. Again and again we are here nearby. So this, by this only we can have a function, and based on that we can find it out, that what are the next alternatives, what are the next data sets, and so on, number of features. So if suppose locality of reference is not supported by some sort of constraints, some sort of data, it means that is poor locality. So then definitely we can see about this. And if there is long run times, okay, so this is again a drawback working with the traditional or general purpose systems. We can find it out that how it can be reduced. So this was just a overview of vector processes. Please allow me to go ahead and we will see how the things work. Now each result, if we are going to work with this vector processors, so each result independent of the previous result, okay, And we implement through the concept of pipelines. Okay. Again, I will refer in the previous sessions, we have gone through the concept of pipelines. We have seen n-level pipelines. So this is very important in terms of achieving parallelism. Now, compiler ensures no dependencies. Okay. So compiler ensures no dependencies and high clock rate. Now, vector instructions, close that. Huh? Vector instructions access memory with no pattern, okay, or with known pattern. So obviously, if you are going to execute this vector instructions, so the memory accessible should be based on some known patterns. And the very important property, I can just write it out. This is somehow a very important property that we are going to focus, and I will elaborate this with the example also. As you can see, single vector instructions implies lot of works. For example, if this is a loop, okay, this example belongs to a high level language C. So suppose there's we are using a for loop, and we are just going to have a matrix, addition. So here the value of A is added to B, and the value of I is taken from 0 to n, and every iteration it is incremented by 1. So that's why it's I plus plus. And the addition AI plus BI has been stored to CI. So being this in a loop format, it will iterate n number of times. Every times the value of AI and BI will be summed up and stored to CI. Now this, as a general purpose computer, yes, we do this kind of programming only, because when we started learning languages and we work out with different matrix part, we have implemented this only. But as a reference to the architecture level, we can have a better solution for this kind of stuff. Let me show you in the subsequent slide. But if it has been a scalar, okay, so we not to be confused about the mathematical terminology of scalar and vector. So because there we have seen that this scalar which has magnitude, and in vector which has magnitude and direction. I'm not particularly about that. Let us see how this can be differentiated. So scalar means one operations. Okay, so that's why very clearly mentioned over here. So this is one operation, and as you can see, if we are going to do this R1 and R2, so we can have the results R3. That is a single instance. And if you want, as you can see, we have a bunch of the rectangles over here, which shows the different instances. So if we have different instances of say V, different instances of V2, so we can have a summation over here based on the operation which is going to perform, and then we can definitely have the different instances in the result. So in this V3, and this shows the result, and we can show the vector length. Okay, what's the length of vector? So as you can see, if we are going to work with an array of vectors, so that can be defined as in terms of vector length also. So here add.vv, this v1 and v2, it's going to be summed up and stored into v3. So that's the basic difference between scalar and vector. So before I shall go ahead, I will check whether there is any question from any of the learners. Okay, so Sukhendra Singh Lodhi, you have raised, so we'll allow you to go through, allow mic. Okay. Sukhendra, can you unmute yourself? Yes, Mr. Sukhendra Singh, I'm audible. Sukhendra, if you have any question, you can please ask. Otherwise, we shall continue. Okay. It seems that you're not getting my voice, it seems to be, but it's okay. So we shall continue with the normal part. And if there's a question, any other learners can raise hand. So they will be given the opportunity to raise the questions. All right. Okay. So I move to the next slide. Yeah. So just now we have learned that vector processing operates on all the elements of the array. Okay, this was the definition which has been given to you in parallel, providing each pass is independent of the other. So see, like again and again, we are touching the same base. So that's why this is very important, because people gets, all the way confused when suppose there has been a dependency and they say that implement in vector. So it's not possible. The thing is that, the instances, the data variables should be independent of the others. And vector processing avoids the overhead of the loop control mechanism that occurs in general purpose computers. So let us see this example. Suppose if this has been a general processing computer system. So if we are going to perform this thing, what I have shown earlier, that you need to perform AI plus BI. And what is AI? Let me show right over here. So A and I may get the value from 1 to 10. Okay, so 1, 2, 3, 4 till 10. So it becomes like this: A1, then A2, and so on till A10. All right. So this is the indexing part of I stand for the index of the vector, and you can have different values from A to 10. Okay, if this has been array, we used to write this only. Now B is the same, is another array variable, and the I value is again. So the purpose is that you need to add these two variables, AI plus BI, and you need to store result in CI. And already explained that the value of I is going to be start from 1. Okay, so the initial value of I is 1 and it moves to 10. This is the values. Now the loop, as all of you understood, that the loop, for loop, or whatsoever we are going to use, will have 10 iterations, and it will start from 1 to 10, and every time it will read the ith instructions and decode it. As you know, every instruction cycle goes through a few phases, and the first phase is read, then it will go for the decode of the instruction, then fetch, and then read the values, and then finally execute. Okay, so read, decode, fetch, and execution, it will go ahead, but it will be go like 10 times. That is a general processing system. And every iteration will have a separate value of I as well as this, sorry, AI and BI. Now, in case of suppose this is the general processing part. All right. Now, in case of vector processing, see how the things have been changed. So you read instructions and decode, you fetch the entire vector which consists of 10 elements. As we have seen that vector length matters, suppose the vector length can process with the 10 elements at a time. So you fetch all the 10 elements of AI and you fetch all the 10 elements of BI. Okay, and then you add up this. So there is no loop in a single instance. You have all 10 and 10 over here. Now you can perform the addition and you can do the result in C. So you can see the basic differences. This happens 10 times in loop. This happens 10 times in loop, and this is without loop. Why? Because it happens in a single instance. Okay, it happens in a single instance. So I hope learners, you got the basic idea that here everything is going one by one. Here in a single instance, we are going to execute all. Okay. Now you may have a doubt that loop itself is one of the very important features of working with the programming languages. So yes, loop and functions, they provide you lots of compatibility, lots of opportunity to work out with different aspect, different solving different real life problem also. But every loop has its own terminologies of complexity. If suppose if you are going to work out with loop, and if you are going to maintain the data structure, what compiler does, so every time you need to retain the different attributes and values of loop. So that is itself, although we have not discussed on that on a very depth basis, but every iteration of loop may consist of the temporary variables, may consist of the register requirement, may consist of storing the intermediate results, may require the value of I, will require the computational part like this read, decode, everything. So every instance of that loop may require its own computational effects, and that require the different complexity issues also that needs to solve. As a programmer, it seems to be quite easy, but as a storage part, we need to work out with different aspects. But here, like suppose we are working to vector, so we get, we doesn't have the syntax of loop over here, and in a single instance, we can have the same addition of AI and BI into C. So in the very beginning of this course, we have gone through the Flynn's classifications, and that was, the base of everything, because again and again the same terminology will be used. Okay, so your subsequent unit is belongs to SIMD, that is single instructions. We'll explore much more of this, and you'll go through the architectural part, the functionality part, the instruction part, all of this SIMDs in the subsequent sessions. So operating on multiple data, okay. So in just one instruction, that is SIMD, single instructions and multiple data, and they are also termed as vector instructions, what we are going through. Now the data for vector instructions are stored in vector registers. So let me write this also, that single instructions, multiple data, that is the core of learning for us. Okay. Now each vector register can store several data elements at a time. Now these several data elements in a vector register is termed as vector operand. Okay, so generally operand means the data or the variables. So once we are going to have a bunch of vectors values, or this is vector length. So every instance or every vector register can be defined as the vector operand. So if there are n number of elements, as we have seen in the previous example, that was 10. So in a vector operand, then n is the length of the vector. All right. Now, supercomputers, as we have heard earlier also, that they have this, these facilities of vector processing, but they also have, n number of features. So let me give the example that supercomputers were evolved to deal with billions of floating point operations and seconds. Supercomputer optimizes numerical computations, that is vector computations, but along with vector processing, supercomputers are also capable of doing scalar processing. Okay, so that is a different area. And later, array processor was introduced, which particularly deals with vector processing. They do not. So it means that we need to understand what are the array processors, because the first example which we have taken of supercomputers, they not only involve the vector computations, but they are also with scalar computations. Now, as we can see, there are few, very important terminologies and characteristics of vector processing. So functionality-wise, first is V to V. Soon we'll elaborate this. Then vector to scalar also. If we can have the third is if we can have two vectors that can produce a vector, and then vector into scalar that can also give V. So it's good to understand that as far as the functionality is concerned, we can have only one this scalar conversion, and we'll see how this thing is going to be happen in real stuff. So each element of the vector operand is a scalar quantity, okay, which can either be an integer, floating point number, logical value, or a character. So this is very important that although you are going to have a bunch of vector length, vector registers, but each one correspond to a scalar. And what do you mean by scalar? So here the scalar may be integer value, it can be a integer value, it can be a floating value, it can be a logical value, or it can be a character. That's very important. So two things you should never forget. First is every element of that vector processing is itself a scalar quantity, and second is we are going to implement everything in terms of pipeline. Okay, this two makes sense. And although the properties which we have discussed, that no dependency, that makes its own importance, which we are going to work out with. the vector processing. So I will just go back to the teams and see the learners. If you have any doubt and at any point discussion over here, you can raise any question to the previous classes also. If you want me to elaborate any of the concept which you want to retake for memory or cache memory or any of the numerical concept also, you can raise the question, or otherwise you can just ask what we are discussing, and then we can go ahead with the remaining aspect. So over to you, students and learners. If you face any difficulty, if you want anything to elaborate over here, just raise your hands and I will try to get the resolve for that. Yes, Sudhir. So Sudhir ji, I will make you the presenter. Yeah, Sudhir, can you hear me?
Yes, sir.
Yeah. So thank you for raising the hand, and I will be very glad to hear your question. Please let me know.
Sir, if I understood it right, vector processing will have additional data hazards. Am I reading it right?
Yes, you are reading it right. You are understanding it right.
So before using a vector processing instruction, say writer of a compiler or those who write assembly code need to do a cost benefit analysis, right?
Yes, definitely.
Sir, any can wondering actually how is it possible to do such cost benefit analysis? Do you need to say in the case of say JIT compilers, you can actually try it out. Here it's it's going to be difficult actually. Once you generate one type of instructions, you need to do performance analysis, etc., in order to change the code.
Yes. So,
So
Sudhirji, absolutely right. I do agree with your point, because as far as like cost analysis is concerned, so it's a little bit the different area that we are not going to touch, but we can take it in some other aspect also. But as far as like the base of your question is concerned, I do agree that just going through on a specific type of data, it doesn't seems to be quite relevant. But you need to touch the other base also, and that is computer architecture perspective. Because once we talk about the CPU or the processors, so they have some limitations also earlier. Nowadays they have been void up in different aspects. One of that functionality which they were limited to go through integer or floating point operations in a one by one instance, or in terms of loops, that has been removed in terms of vector processing. But I do agree with you that you need to have a proper cost analysis basis, and then only you can have the implementation in terms of hardware also.
I think you clarified, sir. Actually, that so before choosing one option, you have to be very sure that you are going to get the benefit.
Yeah, perfect. But as a naive user, we don't do this kind of all that analysis, as you understand, like for a naive user. But if you are going to that kind of structure, then definitely that kind of stuff is required.
Gus, is that actually compiler may provide different optimization levels, and based on that,
Yeah, definitely. And even if, as you say, that compiler may provide different optimization level, but it again originate in number of levels. Because once you go for optimization, it's not only dealing with data types. It also deals with number of structural analysis. Like suppose if you go through syntax and semantic analysis, then we need to see whether optimization is possible in terms of coding itself.
thank you so much for the answer, sir. Yeah, now it's clearer.
Yeah. Thank you,
Thank you.
Sudhirji, for your question. As it's a wonderful question, and I have been very glad interacting with you. Any other students who want to discuss or who want to communicate anything? If you want to, we are not strict to only what we are discussing. If you want to go back, if you want to discuss anything else also, what we have taken in the previous classes, so that will be quite okay for me. So I will see if there is any hand raise. Yeah, fine. So I go ahead and again I will check after 10 to 15 minutes if there has been any questions. So we can obviously discuss. But such a good question by Mr. Sudhir. Okay. So again I come to PPT where I was trying to discuss this. Now there are four features that we discuss. That okay. Now, each element of the vector operand is scalar, we have discussed, and what scalar means that also has been listed over here. And these are the few, features that is mentioned as F1, F2, or O1, O2, O3, O4. Let us elaborate this. This seems to be important because we need to work out on this. So a vector operand contains an ordered set of elements, obviously, which is known as the length. And we have seen just now, we have discussed. So there are four primitive type of extra instructions. All right. So that is mentioned as this V to V, V to S, and V into V to V, and V into S to V. And where V and S denotes a vector operand. Okay. This V denotes a vector operand and S denotes a scalar operand. Okay. Now the instructions F1, F2, they are unary. They are unary because they require a single operand. Just we can have this. And the second one is binary because it requires two operands. So I hope you have heard about this also, that you may have unary, binary. If we have three, it may be ternary and so forth. All right. Let us try to explore what is the meaning of this functionality. What is the meaning of V to V and how come V to S? So this the first functionality, as you can see, which is V1 to V2. It means V to V. It stands for vector complement. Okay, in short, it is mentioned as VCOM. So which complements each complement of the vector is an F1 operations. So the pipeline implementation of F1 can be shown in this figure. As you can see, we can have the input of V1. We work with the vector complement part, and then we can have a vector itself. All right. So this is, do remember that if it is F1, it stands for VCOM, and VCOM is vector complement. The second is vector maximum. All right. So what does it mean, vector maximum? So which finds the maximum scalar quantity from all the complements in the vector is an F2 operations. So the pipeline implementation of F2 operations is shown in the figure. Like suppose if we have say vector V1 and we have different I values are I1, I2, I3, I4, I5, I6 like this, and we need to perform the Vmax. We need to perform the Vmax of V1. Okay, so obviously which finds the maximum scalar quantity, so which is going to be maximum. Okay, like suppose in comparison with this, like suppose I4 is the maximum, so the output is equal to I4. So I4 being itself a scalar quantity. Okay, either it may be a character or logical value or integer value, whatsoever it is, but this is not a vector now, it is a scalar. And as you have heard that a vector is itself in nothing but a group or set of the scalar quantities. So you have given this v1 a vector, and finally we come up with the scalar answer. All right. The third one is a vector multiply, and bit obvious that if you are going to multiply two vectors, you are going to come up with a vector itself. So this is also known as vector multiply, VMPL in short, and which multiply the respective scalar components of two vector operands, okay, and produces another vector product vector, which is a F3 operations. Now the pipeline implementation of F3 shown is figure. So this is just a block diagram overview. We have also seen that how to go ahead with in terms of pipelining operations also. So do understand that if we are going to work with a vector multiply by vector, then definitely corresponding the result will be what? A vector itself, as you can see in this block diagram itself. And it's known as VMPL, that is vector multiplication. So we have done F1, F2, F3. Let us go ahead with the fourth one. And the fourth is scalar vector product. All right. So as I hope you understood this. So there is a scalar number. Okay. And for this, you are going to multiply with the entire V1, which consists of a bunch of numbers. For example, I1, I2, I3, I4. So the resultant of this will be V2 and the V2 will definitely will be, I can say I1 dash, I2 dash, I3 dash, and I4 dash, where I1 dash is nothing but, you can imply this, that it is nothing but as the scalar multiplied by I1 and so forth. Okay, this can be applied for I2, I3, and I4. All right. So this is known as SVP, that is scalar vector product. Do remember, it is scalar vector product. So which multiply one constant value, that is this S value, to each component of the vector, that is F4 operation, and the pipeline implementation of this is shown over here. Okay, and it obviously you may have a doubt that how it's going to implement, because this is just a block diagram. So again, the key lies in the pipelining itself, which we have discussed number of times in the previous sessions. Now we can have two types of vector processors, as you can see. So the first one is memory to memory vector processors, and the second is registers to registers. So in memory to memory vector processors, the operands for instructions, the intermediate results, and the result, all these are retrieved from the main memory, because it's memory to memory itself. So the type of this is memory to memory. All right. So everything is based on the memory. You may be very clear about this, that a computer system may have memory in terms of different aspect. One, we say that register, okay, which is a part of the processor itself. Then we have memory, and by memory we understand that it is based on the primary memory or main memory. If there has been a distinctions of anything, it may be cache memory, it may be anything. All right. So this is memory to memory vector processors, where the operands, the intermediate results, and the result, all these are retrieved from the main memory. Now the information of the base address, the offset, the increment, and the vector length must be specified in order to enable streams of data transfer between the main memory and pipelines. Let me show you through this very simple example. If you're working with a memory, you may have a block. As we discussed earlier, every block has a base address. So this is the base address, and we have the offset. Suppose this is 2, then we can have 4, then 6 and 8. All these things we have discussed in memory. So these are known as offset from the base address 0. Again, you can have a base address for block 2, and you can have some offset from this. Now in this memory to memory, there is no limitations of size, because we have nowadays, all the options of, expanding the memory. So as far as the size is concerned, there is no limitation. But if we have been talking about the register value, then definitely there's a limitations. All right. Now speed is completely slow in this architecture, because if you are working with the CPU, so if CPU is using the register of the processor itself, then it's quite fast. But if you're interacting with the memory, so it's quite slow. And this point has been discussed, in very depth in the previous session. Now there has been some examples of this, that memory to memory vector processors, that is TI-ASC, CDC star 100, Cyber 205. They use this memory to memory format for vector instructions. Now coming to the second category, that is based on the registers. So it is registers to register. Let me go ahead with this. In register to register vector processors, I hope you are very clear that I'm talking about the registers which has been inbuilt into the processor itself. Vector processors, the source operand for instructions, the intermediate result, and the result, all are retrieved from vector or scalar registers. So in this architectures are retrieved indirectly from the main memory using large number of vector registers or scalar registers. So register to register architecture has limited size, because there has been a part of the processors, so always limited, but speed is very high as compared to the previous one that we have discussed, memory to memory architecture. And the hardware cost is high in this architecture, because having a memory, having a main memory is quite easy, quite cheap with compared to having registers in the processors. Okay. Now the examples are CRE1 and VP200 use register to register format for vector instructions. So the objective is that we have two types of vector processors. One is memory to memory, which may come up with advantages. Memory to memory, where there is no issues of memory limitations. There may be issue of the speed, but as far as like storage is concerned, it's not an issue. If we want to resolve the speeds, we can go through the second one, that is register to register, but we can store only a limited aspect of the data. This is a very important point. All right. So again, I hope we have sufficient time. Okay. So I will just check out for any of your question. Let me show you what we have discussed. Then I will take the next part. So we have discussed in this part, we have discussed the features of vector processing. And I have shown you there are four functionalities, that is F1, F2, F3, F4. Okay. This has been repeated over here. And I have shown you the different examples, as well as what's the specific terminology used for achieving these functions. So VCOM is the first one. Second is the Vmax. The only output that we can have in the scalar is Vmax. So VCOM, we have the vector output. Vmax, we have the scalar output because we just find to max one, and vector multiply, that is VMPL, and then scalar vector product. So it doesn't mean that the other computational part cannot be covered. Yes, these are the core of operations, and definitely we can extend to achieve, the other operations as well. Now, next we have discussed about the vector processor, and in terms of memory to memory, and the next is register to register. Before I should take your questions, I may also show this diagram, that modern multiple pipeline vector computers. So as you can see, the first thing we have shown through the scalar processors, that is one by one. Okay. And if we are going to work out with the vector processors, so you can see the architecture point of view, that obviously there's a high speed main memory. We have instruction processing units, and we can have the scalar registers. And in the second aspect, if there has been vector access controller, we can work with vector instruction controller and the vector, registers. But the beauty of working with this is that if we are going to work with the vector processors, we can have, everything in pipelining based on the interdependency that is not supported. Okay. So after this, I am supposed to start the vector instructions. But before I shall start the vector instruction, I will just check out if there is any doubt or any query that we can discuss over here. So that's a good sign that students are increasing. That's good. I hope you are getting the fundamental knowledge, and you're also going through the contents. So it's e-learning contents which has been available in SLM. Fine. Students or learners, is there any questions from your side? You can just raise hands. Okay, so it seems there is no question right now, but I will just continue with my presentations, and then I can again open the forum at last at after 15 minutes. If you have any doubt, you can discuss over there. Okay, you need to raise your hand, your digital hand, and I will give you the presenter, and then you can ask the questions. Fine. Now in this part, let us talk about the vector instructions. Okay, what are the components? What are the format of vector instructions? So the first one is Upcode. It stands for operation code, as you can see over here. So it indicates the operation that has to be performed in the given instructions. It decides the functional unit for the specified operations, or reconfigures the multifunction unit. So that is the operation code. And as we have seen a bunch of format of instructions. So the first part, that is operation code, and the very important is the base address. Okay, and the base address, that from where we are going to get our operands. So base field refers to the memory location from where the operands are to be fetched or to where the result has to be stored. So this is very important and it refers to the designated vector registers. Very important part because until it's not be specified, the thing will be quite difficult to fetch or to store that data. So that is the base address. Third is address increment, address offset, and the vector length. Okay, so vector length, we have seen the examples that it depends on how many instances you are going to work out. And as Mr. Sudhir also asked, one of the very important aspect of working with vectors is the vector length, because if you're going through the optimization area, okay, if you want to perform, then definitely you need to have a clear picture on this vector length, that how much is going to be supported and what should be the computational requirement from this. So address increment, so a vector operand has several data elements. An address increment specifies the address of the next element in the operand. Some computers store the data element consecutively in main memory. Students, you don't be confused about the dependency. This is address dependency. This is not data dependency. Okay, operand is different. For which the increment is always 1, but some computer do not store the data elements consecutively, requires a variable address increment. Okay, it's again a matter of OS perspective, that how and when things are going to work in terms of the locality. Now address offset is always specified to related to the base address. What I said earlier, if suppose the base address is going to be 0, then you are very eager to find out what is the offset. So if offset is 1, it means the elements can be find out as 1, 2, 3, 4, and so forth. All right. So this is a numerical value. Okay. Numerical, you can say memory mapping, which maps to the value. 1, we can have value 1. Then this 2, we can have value 2, and so forth. Okay. So the effective memory address is calculated using the address offset. And the very important is vector length. So vector length specifies the number of elements in a vector operand. It identifies the termination of vector instructions. Now, how to improve the performance? So we come across two overheads. The first is setup time, very important aspect or characteristic during working with vector processing. And the second is flushing time. What does it mean? So setup time means when the vector processing is pipeline, the time required to route the vector operands to the functional unit is called the setup time. Okay. So it's again what you said, that we need to have a computational analysis of that. So that is the setup time when we are going to work with vector processing in this pipeline also. So the time required to the route vector operands to the functional units. Okay, that is a setup time. And the flushing time is the time duration that a vector instruction takes right from its decoding until its first result from the pipeline. Okay, as we have seen that if we are going to work like this, and along with suppose pipelining also, it's work like this. So when the first result have been achieved, that's very important. Like suppose we are getting this first result, this is the first result. Okay, so that may be taken as the time duration that a vector instructions takes right from its decoding until its first result is out from the pipeline. So if this has been the resultant part, let's get out, that is the time duration. So the vector length also affects the efficiency of processing, as the longer vector length would cause overhead of subdividing the long vector for processing. So there are four very important features. So we can improve the vector instructions by reducing the memory access, okay, and maximizing resource utilization. We can also integrate the scalar instructions. The scalar instructions of the same type must be integrated as a batch, and it will reduce the overhead of reconfiguring the pipeline again and again. And what kind of algorithm we are going to use, although it will be beyond the curriculum, if we take the examples of algorithm. So choose the algorithm that would work faster for vector pipeline processings. And vectorizing compiler. So obviously the role of compiler is very, very important when it's going to be integrated with the concept of vector processors. So a vectorizing compiler must regenerate the parallelism by using the higher level programming language. Okay. So let me have a recap what I have talked about, that if we need to improve the performance, so we need to improve the vector instructions wherever it's possible, through reducing the memory access and maximizing the resource utilization. Second, we have talked about this was number first. Number two is integrate the scalar instructions. Third, we have talked about the algorithm part, that select, like suppose if you can say both algorithm for multiplication. So we have seen it has optimization with compared to the plain algorithms of multiplication. So that kind of strategy we need to work out, although it may require its own understanding of the base algorithms. And the fourth is vectorizing compiler. So it's a role, a very important role of the compiler itself, that how it's going to be perform the vector operations. So as you can see, if we are going to improve the performance, and in advanced programming level, the four stages are identified in the development of the parallelism. Okay, so the first one is the parallel algorithm, number one. Second is which kind of high level language you are using. Third is efficient object code, that is O. And next is the target machine code M. So we have seen four aspects: A, L, O, and M. A stands for what is the parallel algorithms. You are not supposed to be confused with distributed algorithms. They are the different domain. How we are going to achieve the parallelism in terms of software structure, that is parallel algorithm, that is A. What kind of high level language we are using, what are the threads which has been supported. As we have seen in the very beginning of unit 2, where we have discussed about the parallelism, we have also talked about like based on the language complexity in terms of high level, how the threads can achieve that, how we are going to implement the concept of process in multiple threads. That's very important. And efficient object code, very important. And the target machine code. All right, now in the ideal situation, as you can see in the last part, the parameters are expected in the order this. What is this? So A should be higher than L, that higher language. It's higher than O, and it's higher than M. So this is one of the things which has been expected to be in this order. That makes the things quite competitive, quite competent. So let me have a recap what we have understood till now. We have understood that computers having vector instructions are vector processors from where we started. Vector processors have the vector instructions which operates in a large array of integer or this floating point numbers, or logical value of characters, or all elements in parallel. That is known as vectorization. Vectorization is possible only if the operations performed in parallel are independent of each other. I have talked about this, in a very important manner, independent of each other. Operands of vector instructions are stored in vector register. As we have discussed, a vector register stores several data elements at a time, which is called vector operand. All right. Now, next part, we have discussed that a vector operand has several scalar data elements. Obviously, vector has been formed in terms of scalar elements itself, like this. A vector instruction needs to perform the same operation on the different data set. Hence, vector processors have a pipeline structure. Now, vector processing ignores the overhead caused due to the loops, which we started from the very first example, that there will be no loop in case of vector processing while operating on an array. And we can improve the vector instructions by reducing the memory access and maximize the resource utilization that we have discussed just now. As you can see, this slide I've taken from the second unit, which we have discussed, that it's not only a matter of implementation in terms of vectorization. It's also a matter number of other issues, like suppose if you are going to work with different processes, and suppose this has one of the single thread that is part of process. Now it really matters whether the operating system or the compiler structure, whether it's going to support multi-threaded process or not. Then only we can perform with different levels of vectorization as well. So this is the next topic of working with SIMD, okay, where we need to explore what happens in different, serial executions, that is one by one, or what happens in the parallel execution, that is known as a true parallel achievement. Okay, if we have multiple CPU and we can execute the different tracks of T1 or T2, T3 on a parallel manner if the problem has been given. So these two diagrams are the very basic diagram that has been referred from the contents provided to you. But before I shall go ahead with the subsequent topics of SIMD architecture, I will see the forum, and if any student has any questions, so they can ask. Okay, because we left out with the time, so I hope we can also discuss bit of this, and we'll take the remaining in the next session. But unit number 10, that is the next class, will be based on the understanding of the different aspect, different level of this single instruction multiple data, and that's the core of working with vector processing. So as you can see in the slide, that the parallel execution, it's based on a number of instructions and data streams that can be processed simultaneously. And this is the Flynn classification. It has four aspects: SISD, SIMD, MISD, and MIMD. So we are a bit concerned about the first one, that is single instructions and multiple data stream, where you can see over here that SIMD belongs to vector processors, fine-grained data, and obviously we perform the parallel computation also. So this is very important because if you are learning this course of computer architecture, you must be have a crystal clarity about all these classifications with a proper understanding of the architectural view also. So in next session, we'll discuss about SIMD in more depth, along with the different operations, the different formats which is supported by SIMD structure, and we'll see how it overcomes the drawbacks of this. I have a one slide which I will show you now, where already this has been discussed, but let us go through this. That if we have this bunch of as instructions, so these are the instructions as you can see over here, and the next is data. So this is the data part, and this is the result. So we have, if we have the SISD, that is single instructions and single data stream, so we can have this as one time instructions and data, and then we can have the result as well. But if we just shift to SIMD, we stand for single instructions. So instructions again same, right over here. This is the instruction. And here now we have multiple data, and then obviously working with this kind of structure may have bunch of benefits. As you can see, the result is like this only. Okay, so we can have results as well. So it has many features that we'll figure it out, we'll discuss. So a normal CPU operates on these scalars, which is one at a time, but a superscalar CPU operates on multiple scalars at a given moment, but it executes a different operations on each instruction. Otherwise, in the second part, a vector processor lines up an entire row of these scalars, and obviously you have seen that we can have multiple aspect of result also. So learners, we will explore much more in the subsequent units in the next online session, that is SIMD, and that will go ahead. Although we are touching, the closing part of the sessions, but I wish that you may please go ahead with all the contents which has been referred in this session. And if you feel so, you can raise any of the doubt in the learning forum, where I'll be more than happy to go through the resolution of the queries. And we will take over this session with SIMD in the next part, and we'll also explore the different formats of instructions that is supported by SIMD. So with this, I thank each one of you for being so active in the class, and I will just see whether there is any question so we can have a discussion right now. So I can see that there are lots of students, but question I cannot see. So thank you. It's okay. You may see and you may revise the contents. And thank you, Sudhir ji, also for raising the question. And if you feel so, any question, so that may be taken in the subsequent sessions also. Thank you so much. Over to you, ma'am.
Thank you, sir, for such an informative session. Now, still learners, if you have any doubt, you can post it on the discussion board. And please do participate in the general discussion of their respective practical sessions. Okay, thank you, everyone. Have a nice day.
Thank you, ma'am.